Okay, so thank everyone for joining today's presentation. So today, uh, Long Long Jiang will be presenting an interesting paper um, on knowledge distillation for developing next generation ecohydrological model. Long is currently a postdoc researcher at University of Washington, and he had a background in ecological modeling and hydrological modeling. He got a PhD degree from the University of Hong Kong, and he has been studying the eco-hydrological problems in the US when he joined University of Washington about 2 years ago. So let's have Jiang start his presentation.
Yes, thanks, Yang. Thanks for the invitation for sharing my work. And this is a work with my colleague from the University of Washington and some of my peer members and some of my colleagues from the University of Washington and uh, Cochin. And right now I'm a postdoc, as Yang said, in uh, University University of Washington. And today my topic is to uh, the title is Knowledge Distillation for Next Generation Ecohydrological Modeling. And you can find the preprint in archive here. And let's start. As we know, ecohydrological modeling is a very useful tool to simulate the ecological and hydrological process and try to is it very essential to understand the uh, dynamics of a complex environmental system. There will be two different methods for the modeling. First is process-based models. It can have the advantage of the physical resilience and the interpretability. Predictability. Uh, for example, here in the right figures, I will show a very simple hydrological model called a bucket model. It involves a precipitation, evapotranspiration, and a stream flow. When we add some biochemical processes, it will involve more parameters, which make the calibration more difficult. And when we use some division algorithm to transfer the lumped model to some distributed model, it will increase the computation cost significantly. And finally, when we use some package programming language to package such equations and such process-based functions into a existing or mature model software, it will make the model structurally rigidity and have a limited scalability. That's their disadvantages. Another method for ecological modeling is using the machine learning. Um, the machine learning model will have advantage of computational efficiency and flexibility. Right figure shows an example that we use precipitation temperature as inputs, and through training and training the machine learning model by observed data, we can got some results related to like the stream flow and the nutrients, nutrients relate outputs. But the problem is normally the machine learning model can is regarded as a black or gray box. They will have a limited interpretability and transferability. That's mainly main problems. And also the machine learning model will lack the physical consistency and when the new scenarios are included, it is very hard to use existing machine learning model to provide such new scenarios. We need to retrain the model, and that will make the model performance uncertainty. Right now, we understand that both the traditional process-based model and also the machine learning model, they have their advantages and the disadvantages. So there are some emerging research that are focusing on the physical informed or the physical informed neural networks try to bridging these two worlds together and to explore some hybrid approach. For example, they can apply some constraints to the loss function, for example, the mass balance and the energy balance, and they can also directly embedding some equations into the machine learning layer, or they can apply some specific design into machine learning layer, try to achieve the combination of process-based model and the machine learning model. But we envision that future model and the ecological logic will be will be much broader than that. The explicit constraints only capture only a small part of such knowledge. More broader expertise should include a cognitive framework. For example, the heuristic method, reasoning pattern, and the decision rules that build up from the decades of experience of experts. But due to the technical barriers, because most of the model users, they do not have the strong background of the computer science, that prevents them from transfer the knowledge into a into reusable model resources. Since we envision the future ecohydrological model that can automate the workflows and provide a transparent experience, so it is very important to embedding cognitive framework into AI. But it requires a systematic methodology for extracting and embedding both explicit and implicit knowledge into a modular and transferable AI architecture. To arrive this goal, we propose a three-phase knowledge distillation framework. Phase one will be the behavior distillation of existing models. Now, phase two is the structure distillation, try to unify different process-based models. And phase three is try to embedding the is a cognitive distillation, try to embedding cognitive framework into AI architecture. I will introduce one by one because this is also progressively pathway for towards to the next generation modern system. The phase one will be the behavior distillation. Process-based model is already widely used in many cases and many projects, but there will be two main changes of such a process-based model. First is with including more and more biochemical and some related processes, the parameters of a process-based model increase a lot, which makes the calibration very difficult and very hard to evaluate the performance of the calibration and whether parameter set is good or not. Another is with a finer resolution, especially for the distributed model, distributed hydrological model, the computational cost increase significantly. So the phase one is trying to provide a programmatic entry point that combine machine learning with a process-based model, try to provide a model user approach to make a full use of the computational advantage of the machine learning model. For there will be two steps for the behavior distillation. One is model simplification, and then use a machine learning method to enhance the model simplified. In the model simplification, there will be two main methods called resolution coarsening and process reduction. It is aimed to create an efficient variance that at the same time preserving essential process fidelity. And then we will use the simplified model to generate some data for train a surrogate model, train a machine learning model. Then we go to the step 2, use the machine learning method like the transfer learning, residual learning, or combine these two together to improve the predictive accuracy of such a surrogate model and improve the system behavior application. Here, I will show a case study result in the summation for the case for the demonstration. So the summation watershed is a watershed that in the northwest of the America. It contains different kinds of land cover, different land use, and is perfect for the demonstration. The focus variables of the demonstration will be the stream flow and then also the nitrate loss. The model, two models are used. One is a semi-distributed model called SWOT, and another is a fully distributed model called VERMA, Visualization Ecosystem Land Management and Assessments. It is developed by EPA. And for the model simplification and resolution coarsening, it will decrease the HRU of SWOT from about 2000 to about 200. And coarsening the Verma's grade from 30 meters to 360 meters. For the process reduction in the hydrological part, it will be replaced by a HBV number model. For the nitrogen part, it will replace with a simplified nitrogen cycle module. For the machine learning part, it will use transfer learning, residual learning, and combine these two together. The machine learning model used is a multi-layer STM for all machine learning models here. So the right figures, time series figures shows results from the original process-based model of the HBV, from the SWOT, from the VERMA. We will use the first half period as a data training and the last half period for the prediction for evaluate the performance of the model. Here is a comparison of different behavior distillation strategy. We will use a matrix called a composite score. It is an average value of NSE and KGE for evaluate the performance of the predicting accuracy, and use the total runtime, including the training time and the predicting time, for evaluating the model's efficiency. From the pillar figures here, almost all for example the blue and red one, almost all models can predict where in for the rainfall runoff. And for the new nitrate loss, the situation change. You can see the especially for the VERMA, you can see the brown pillar here, brown bar here. For the direct surrogate model, it perform not so good. And for the models that combine transfer learning and coarsening, it perform more stable and higher performance metrics. You can also directly see the result from the left for figures, time series figures there. You can see for the flow prediction, almost all different models perform very similar. And for the prediction for nitrate loss, they will show different performance. The original model is the blue line. Original is a direct surrogate. It performs not so good. And the green dashed line is the combined transfer learning and cross-learning. It performs much better and stable than others. When I talk about the efficiency, the direct surrogate will be the fastest, since you can see that the time is very short. And the cross-learning is very time consuming, is a highest cost, and the main cost is happened for the data generation. And the hybrid method, a hybrid strategy combine residual learning and transfer learning together. We've got a balance between the efficiency and the accuracy. Here is a simple summary that for some simple process like the stream flow and the soil moisture, maybe the direct surrogate model can also capture the long-term dynamic wear. But for the complex process like nitrate loss and with strong map difference, it needs a specific distillation strategies. And a hybrid approach combines residual learning and transfer learning and resolution cross-learning and process reduction. We got a balance between the accuracy and the efficiency. Overall, the behavior distillation can enhance process-based model with a higher efficiency in their computational cost, and it can also focus further enable the faster calibration and scalable watershed applications. The phase 2 is structural distillation. Although in phase 1 we have developed an approach that combine a machine learning model with a process-based model. But our problem is that there are so many process-based model where it is very difficult to develop a machine learning model or surrogate model for each process-based model. That means different process-based models, they have their Unicode framework, Unicode design, and even they have different programming platform that limit their cross-model interoperabilities. Thus, in this phase, we will try to provide a unified GNN-based approach, graph neural network-based approach to abstracting different process-based model. Here's how the graph-based structure works. We will use user nodes to represent the special units for the areas for the units with different characteristics in climate, soil, land use, and maybe topographical attributes. For example, the lumped model like the HBV can be regarded as a single node graph. And the semi-dispute model like the SWOT, different HRUS can be regarded as multi-node direct graph. And for the fully distributed model like the VERMA, it can be regarded as a high-resolution grid graph. And the structural framework uses edges to describe the interaction between different nodes. For example, their flow paths and their material or the mass transport, and even the ecohydrological in relationship between different nodes. And through the graph cross-learning and non-cross-learning, we can easily switch from different types of models. And finally, the models can updates each node's state by aggregating the information from their neighbors. and apply update equations for the update the state. The updated equation can use the method like process-based equation, and also can use some maybe machine learning layer or deep learning layers, and can also hybrid them together. So to implementation such graph-based framework, I've developed a PyTorch-based toolkit to enable such a seamless coupling of physical process equations with machine learning models in a end-to-end transferable trainable system. You can find the toolkit in the GitHub, and it is very easy to use, and you can also install the package. It is also published in the PYPI. You can install it directly. It is very user friendly, and the toolkit consists of 4 main parts called updater, trainer, data manager, and visualizer. The updater is the main part of the toolkit and main part of the model. In this part, the model user can easily design their own updater with using their equations or some machine learning layers or some hybrid strategies. They can just write down their equations. That will be very easy to apply. The model user, they don't need to have a strong background of computer science, and they can also use um, tools like ChatGPT or some other large language models for generate the updater according to the module specification. The trainer will provide a differentiable training with 4 distillation modes for knowledge transfer. The 4 modes are calibration, training, extraction, and transfer. It actually depends on what data you used for training and what you want to train. For example, when you use the observed data to train a process-based updater, that case also can be called as traditional calibration. And when you use observed data for train a machine learning updater, called traditional training. When you use a process-based updater to train a machine learning updater, that's called extraction. And when you use a process-based one process-based updater to train another one, that's called knowledge transfer. And the third is the data manager. It is mainly for the data processing. And also another important function is graph coarsening. You can see that the original graph can be changed to the coarse graph and even changed to a nodes graph by the data manager. And finally is visualizer. It is try to provide some time series plot, performance metrics plot, and some special maps for evaluation the performance of the models. Here is also a case study result for demonstration. Also, same watershed, the summation. The top right 2 figures A and B is show the nitrification results from the process-based model VMA and from the ecohydro model I've developed with using the updater from the diagonal equation. You can see these 2 figures have a very high spatial consistency, which means that the ecohydro model can reproduce the results from the process-based model. And you can also change the updater for example, replace the updater that mimics the Weimar to some other process-based equation like the pattern equation, and can also change to some simple machine learning updater. Here is a MLP with 4 layers and 64 units, and you can also switch to a hybrid updater that combine patterns, equations, and MLP together. You can see these 3 figures shows the prediction accuracy of the new updater suite that replace the original unification updater. And the warmer color represent the higher prediction accuracy or higher consistency. For the process-based model called pattern, it can also provide a good accuracy with more than 0.6 score. And for a simple machine learning updater, in some area, the warmer area, it will provide better prediction results than the process-based model. But for some other area, the dark blue one, it will provide the performance is not so good, which means that the stability of the machine learning based model is not guaranteed. And combine these two together, the predicted accuracy become much better. Can and also make it more stable. So to summary, a simple summary, the ecohydro model can provide a module flexibility because model user can easily design their own updater for their project, and this toolkit provide a physical AI integration and a scalable efficiency for complex watersheds, and combine the process-based model and the machine learning model updater together to provide a hybrid updater will increase the prediction accuracy overall. The phase 3 is the cognitive distillation. We imagine that the future modeling system should automate the workflow, mimic the expert, which means that it requires with formalizing implicit expert reasoning and modeling assumptions. And so we would provide a EBHM framework, try to emulate expert modeling from workflows. That's called eyes, brains, hands, and mouth. I will introduce it later, but at first we'll try to understand why we need a cognitive distillation. There will be mainly 3 problems in current using of machine learning and a process-based model. First is limited human expertise. The domain knowledge in ecohydrological modeling, it keeps evolving, but the models cannot keep up. Many literature papers and books comes out with new funding, but the continuous updates and the integrating of such knowledge still depends on the limited individual expertise, because most model users, they do not have a strong background of the computer science to develop a mature or mature model for their project. So, but AI can help with the model development. Another problem is path dependency bias. When we working on a project, model selection is very important, but it is often shaped by precedent, because we are so lazy and we try to use models that we are familiar with. we try to use we are limited by the historical asset rather than use the scientific suitable models, and they will affect our decision making quality. But AI can help for the model selection because you have a better understanding of a general models that can be applied for a project instead of considering the historical models that used in a project. And third problem is the incomplete understanding of the underlying process and underlying laws. Normally, there was many evidence and papers evident that incorporating new process into a modeling system or existing model system can probably lead to some unrealistic system behavior. Expose our understanding in the underlying process or the laws is incomplete. But AI can help finding the hidden laws in the data. To summary, AI can help provide or offer a new pathway to overcome such limits through cognitive learning and adaptive reasoning through three steps like the learning the cognitive frameworks and emulating the expert reasoning and create an involving intelligence. Here is EBHM cognitive architecture developed for the phase 3. And this architectures describes the capability of expert hydrological modeling agent should have. It is mimic the human expert with four different main parts called eyes, brain, hands, and mouth. The eyes is for perception. Will integrate different kinds of the data and code and domain knowledge, even from literature, from papers, from books, from user manuals, and from diverse sources. Try to understand more about the domain knowledge. And the brain is mainly for the reasoning. It is tries to understand what is the domain knowledge is, and build up a structured knowledge graph, and then apply reasoning with a continuous learning and adaptation. And hands is for execution. It's mainly for the model running. It will use a model agent workflow system, and maybe for the goal-driven modeling and generative planning. And mouse is for communication. It is aimed to generate some model outputs and provide some explanation of the results. Maybe provide some reasoning playback for interpretability. Here, I will show illustrate a simple workflow for some short sheets to illustrate how we use autonomous modeling system for the nitrogen loading mitigation planning. Since it is still on the conceptual stage, it is an image of the future workflow. And at the beginning is a task initiation through the chat with the agent. We can define the objective and some metrics and decide a execution plan for the whole project. Then the agent will try to acquire different source of data. For example, for data from the NOAA about the weather data, and the stream flow data from the ESGS and some other monitor data from the state monitoring station. And third is strategy generation. Based on their knowledge graph, the agent will try to generate some mitigation plan, such as maybe 15 or 30-meter riparian buffer, and many other plans based on the domain knowledge. And then will be the batch simulation running. The agent will try to choose or assemble models. For example, they can assemble the module updates from the ecohydro model we developed in last phase, or they can use some API provided by some existing models, try to assemble this model together and batch running them with multi-objective evaluation and closed-loop refinement until they reach their targets. And finally, the project the agent will deliver some results, for example, the tables, maps, and also a very important part is reasoning chain for reproduce that decision, for just a playback of what the agent doing and try to reproduce it. Although the three-phase knowledge distillation is rooted from the ecohydrological modeling, but it can also be applied for other domains. For example, the behavior distillation is trying to build a simplified model variance and try to use that simplified model to enhance increase the computational efficiency. That concept is also can also apply to some domain with high computational modeling, high computational cost modeling, like the atmospheric and ocean circulation and the land atmosphere interaction domain. And for the structural distillation, it can also be expanded to urban water system, river network, and transportation flows, and even power grids, unless such a system can be transferred into a graph. That means they might have defined a spatial or logical topography. And the cognitive distillations for many workflows in cognitive distillation is very general and can be applied in many process-based domain, including their expert heuristic modeling strategy, decision rules, and the EBHM architecture can be also used for such domains. And through combining foundational models like the Llama 3 and Mistral with some domain-specific fine-tuning, this framework, the EBHM framework, can establish a unified intelligent modeling agents across different domains. To conclude, this paper or this work is try to provide a scalable pathway towards intelligent model system. It is aimed to maintain the physical consistency and towards to an autonomous expert level performance. In the phase one, we try to provide immediate benefits for the model user to enhance model efficiency. It is a programmatic entry point for the model user. And structure phase two is a structure unified. It will try to unify different process-based models, provide a platform for different models to compare with each others, and provide a platform to incorporate machine learning model and easy to use. And it is also a foundation of the future autonomous intelligence, where the AI can help can use the ecohydro model to assemble different modules together for future serial setting. And the final is autonomous intelligence use AI and emulate expert reasoning and for the decision making and continuous improving of the system. Yeah, that's all. Thanks. Any questions or I will show.
Sorry, my audio was off. I was just saying thank you for that, and let's open it up for questions. Yeah. So I guess I can start it off. So you showed a three-stage process, and you have actually done some experiments on the first two stages.
Mm-hmm.
So could you say maybe a little bit about your plans for how you plan to explore into the third stage? Yeah.
Yeah, the third stage, right? Yeah. Actually, the third stage is a conceptual stage right now, a conceptual stage,
Sure.
and it will be I think it will be a long-term research direction. I said that, and it's actually require a large number of technical development in different aspects. For example, we need higher reasoning ability of the large language models, and we need to do the fine tuning of the general foundation model based on the, for example, the Llama 3 and the mystery. And my future working will focusing on provide AI protocol type and with a very simple AI agent focusing on provide a simple workflow using AI combining with ecohydro model at the web. I think it will take a long term, but for some simple case, we can try to get a simple case in the future.
Sure.
Yeah.
In part, I'm asking because Antoine, you were working with the equivalent sort of language models or something to do something related to knowledge distillation. Am I not correct, Antoine?
Yeah. I'm right now doing that.
Yes and no. Um, I'm working with large language models for sure. My perspective is more using agentic design to focus on the process of human decision making. So there is some aspect of knowledge distillation, but it's at this point it's a bit more focused on trying to first leverage the full capacity of LLMs that is believed to be inaccessible because of monolithic design that basically resulting from limitations in the data retrieval mechanism. We estimate that we are not yet able to access the overall knowledge of LLMs. And the theory about it is that multi-agent system with different persona and generating some sort of synergistic interactions between agents are able to better access the whole of the knowledge of an LLM that can be modeled as a big probability distribution over the next token. So my focus is that more, but knowledge distillation and everything that stems from it is definitely some of the next target that I can't say too much about it yet, but it's in the pipes. I can say that.
Sure. So going back to what you said, the hypothesis you're working with is that by forcing the LLM to take different perspectives through the prompting mechanism, that helps you to query much deeper into its knowledge base than if you take a very general perspective. Yeah. Okay.
Yeah, it's been proven. It's been proven lately in a paper, a 2025 paper, I think September or something like that. And basically, what they do is they find a proxy method for performing partial information decomposition on specific sets of problems using multiple agents, and they're all able to show the emergence of synergy in the case where, while in certain contexts with certain agent groups, certain agent profiles, and certain group sizes. The whole point of that study was to show emergence of synergistic information creation by agentic LLM compared to monolithic implementations. That was some sort of a proof of something I theorized. I didn't have any proof. It was just a hunch from what I was doing with LLMs. But this is getting more and more interesting. I've seen recent approaches to apply mutual information approximations to token representations using HSIC method. I can't say much about it, but it's just like a bunch of math that is approximate mutual information in a probabilistic way, and it's a kernel-based method. So there are some limitations, which is the choice of a kernel and the choice of the parameters of the kernel, etc. But they were able to show some promising results on computing mutual information from token representations. And because it's a kernel-based method, I theorize it can be extended to kernel matrices. So you could do it with kernels with token sequences instead of token to token. So that would be an entry point to approximating mutual information between sentences in the context of an LLM. Of course, from that, there are other problems, which is if you use a big intelligent model from an API, you can't not access latent representations because it's a lot of I/O overhead. It's a lot of computation overhead. Like providers don't want you to like have the embeddings. So you have to run a local model or you have to modify something. And when you do, well, then you have to process a bunch of very high dimension vectors on top of words, but that's another issue. But the point is, theory is making progress on this, applying some information theory to quantify the informational value of LLMs. And I feel like this is intrinsically linked to agentic designs. Yeah.
It just sort of, as you were talking, it sort of occurred to me that something when humans want to access information that's stored, one of the tricks we do is put ourselves into different states, right? Like if you want to access information regarding sports performance or something like that, you might put yourself into, I hesitate to call it a hypnotic trance, but a kind of a trance state.
Yeah.
And then that helps you access that kind of information. And I'm wondering if this has something to do with the fact that there's just such high information density that you almost have to necessarily prompt in different ways without which it's sort of impossible to get that depth of access. It just the analogy seems very strong to me.
It's a very good analogy. I think there is a difference though, which is we have full control over what we do with LLMs, but we don't have full control about what we do with our brain. And I think even in this day and age, there is still a lot that is yet to be explored. We don't know everything, which is a bit depressing when you think about it. But there is still a lot of things we have to learn about the functioning of the brain and memory and all that. But this is definitely true. We know, I'm pretty sure that we are conscious about what we are conscious about what we know is actually only a fraction about what we really know. There's a lot of stuff we just access subconsciously and yeah.
Hmm.
In the same way that and I feel like it's also true for like what our brain does unconsciously is very hidden to us. It's just a natural hunch. Again, there is nothing proven about this, but a lot of people, you know, talk about instinct
Yeah,
and having hunches and that kind of stuff. To me, it's just a subconscious processing of signals that we interpret, but that we are not conscious about interpreting. We have hunches about this,
sure.
and we noticed something, but we didn't. Well, we unconsciously did. I feel like memory works the same way, and our brain is just protecting us from maybe too much information and processing it differently. I don't know.
Right. No, as Long was talking about his third, the cognitive distillation, it just sort of reminded me that the stuff you were doing was, in some sense, very similar. Or not similar, but you know, with the similar end in the sense that you're talking about using multiple agents and then using workflows to somehow organize and use agents to help organize that information in some strategic way. Yeah.
Yeah.
The other question
I
that
can.
came up for me, sorry, go ahead, Long. Yeah.
Yeah, I think you're right. And the EBHM is just a framework that mimics the humans experts and try to use the model agents that limits the ability of the general foundational model, that because you do not control what the general models, natural language models can do. So you need to make a framework and use a promote engineering to control the performance of the natural language model and make the workloads perform as you wish and make it really can be used in a specific domain. That I think that's the
Sure.
most important part. Yeah.
The other thing that occurred to me as you guys were talking was that the language that we use when we communicate also prompts in a different way, right? So if I were to use language which was very used a lot of sports jargon, for example, which only a person who is deeply into sports would use, then presumably it would access the model in a very different way than if I used language that a scientist would use to prompt, or language that you know, we the point is that the way we talk, the words we use, give information to the system in a different way. So if a person, two different people could ask the same question and get two completely different answers just because of the language they used when they formulated the question, I guess. Yeah.
Yeah, that's what I was saying. So you cannot control the outputs of the natural language model when you do not have a exact framework, and even the very similar problems from two different people's asking the natural language model maybe provide very different outputs, and you cannot design and cannot decide which one will be better than others. That, yeah.
Right. Allison has a question there. You might read it out. Oh, I can read it here. Allison says, I'm in a loud room. I was wondering if the three phases are highly connected or sequential, such that once we reach phase 3, we always end up cycling back to phases 1 and 2, say to inform the model after a soil scientist got some new data and understanding, or once we're in phase 3, is that it and it's all in the AI system?
Yeah, I think it's yes, good questions. Actually, phase 1, phase 2, phase 3 is progressively stages. And right now, maybe in the future, we can imagine that in the future, maybe when we reach the phase 3, we might not need the phase 1 and phase 2 because the agent can help us to complete the work in the phase 1 and phase 2. But right now, so many limitations. Actually, it's a transfer age, I think. We still need the process-based models for some for some projects. That's why we need phase 1 to enhance the performance of process-based model, just to provide an entry point for the model user. Because many traditional ecohydrological model user and even many traditional process-based model user, they do not have a strong background of the computer science. Even they might know about the AI, but they haven't used about that. And machine learning is also emerging direction and application in the recent years because of the rapid development of the GPU. So there are also many limitations of current in the current stage. That's why we still stay at the phase 1, and that's an immediately benefits for the model user in phase 1. And we can get a balance between the machine learning model and the process-based model. And phase 2 is what we want to we try to do in the future, because we have different process-based model. We have different equations of different knowledge from literatures. We don't want to waste our finding in the last. So we'll try to unify and make more model users can use that knowledge and compare them together. That's just to provide a platform for that. I think this tool will be the fundamental work for the phase 3. When we develop a unified platform, and then that platform can be a promising platform for the future AI agent, because model agent, it is also very difficult for agent to use the API from different model, because for example, the SWOT, Velma, they do not provide an API, and it is maybe hard for them to provide API for the AI agent for operate that. So when we provide an ecohydro model and involve enough process-based equations, I think that will be also used for phase 3. So for your questions, in phase 3, we might don't need phase 1 and phase 2. Yeah, thanks.
Okay.
For what it's worth, lately there's been a lot of development onto two major technologies, which are called MCP, Model Context Protocol, and A2P, Agent-to-Agent Protocol. And basically, this is the equivalent of an API for AI agents. The statement is, we have developed LLMs and they're very smart at doing things. However, if I ask Siri to book me a Uber, it still can't do it. And why? Because we have to go through an API that is exposed by a developer to access specific functions, and that takes a lot of individual specifications. And the posit is, now that we have AI and they're really smart, can they navigate human interfaces and understand the functioning better without having to resort to APIs? And from this stemmed MCP, so that's a specification you can develop when doing AI agents to specify how they can talk to other AI agents in order to make all LLM or agentic based LLM systems communicate better with each other. Basically, you could see it as a new version of what an API is. Instead of software run API, AI and agentic AI run MCP. So assuming that with the announcement of OpenAI, ChatGPT apps and everything that will be similar in the couple years to come, maybe in 5 or 10 years from now, the traditional software will have been replaced by AI. And if that's the case, MCP will be the new API system. So As you said, there
It's
is
like a
no
hand.
API for AI agents, but there is something that is long. There is something that is getting in the same way.
Yeah.
It's like
Yeah.
having a handshake protocol of some kind, right? It's like everything needs to know how to
Yeah.
talk.
Yeah, this is a specification where basically it's some sort of a you describe an offer and a demand, what you can exchange and what you can give and what you can receive, what sort of services
Mm.
you provide and what you can benefit from, some sort like that.
Mhm.
But I mean, I haven't used it too much, so my knowledge about it is like its use, but I haven't really used it yet. I'll need to come to it at some point, but yeah. It seems very promising, and it's been a major shift in the LLM agentic community. If you look at the issue tracker on GitHub for Google ADK and the emergent agentic frameworks for LLM, when MCP was starting to get implemented, it was inundated with questions and issues and stuff like that regarding MCP and A2B. So this is really becoming a central point in because the first step was getting AI models out there, showing the people that it works and it's awesome and it's getting better and better and better. But second step was very well summarized by the Sal Altman during the introduction of GPT apps. It was like 2 weeks ago for a keynote held at by OpenAI. And now it's how do we market it? And it's putting LLM at the center of an app creation system and because they have a lot of in-between interactions with various data, various other models, various things, there needs to be a protocol for communication. And API is great for software, but it's inconvenient for AI agents, so they devised something else.
Yeah.
Okay.
Yeah, great. And I have also found um company like the a Cursor, a company that developed for some MCP work. They have developed some just like a manual for how we design the promote, how we design, how we tell the large language model to work. It's a standard. It's not like API. They have a very detailed description of the function, but the MCP is very promising and decide a standards that for agent and for large language model to understand. It is not so strict, but more flexible. And I think that it can apply in different agents and very promising work.
On top of that, this is not the first attempt at specifying protocol for communications for agent. I don't have the name. I think it's AFib or something like that, but I could find it eventually. But there is like a protocol that is older and that just dealt with basic agent. It was before LLM even existed. I can't really put a name on it right now, but it's definitely not the first iteration of agent communication protocols.
Sure.
I can find it. I know where it is.
Okay.
This is cool.
In the meantime, I had another question. In your part two, phase two, you talk about converting everything into a graph neural network with communication amongst graphs. I'm just curious what you can say about how do you what mechanism is used to decide whether to refine the graph to make it to add more nodes versus coarsening the graph and removing nodes? How is that how is that operational decision actually made?
For example, for the uncoarsening, it can use a replication or the interpolation from
No, that's the
different.
mechanism for doing it. But how do you decide when you need to add nodes and when you can remove nodes? What's the sort of logic behind knowing whether to coarsen or to refine?
There will be an algorithm called Gragnik that they will this is a mechanism combine. It's actually a community algorithm. Try to find out most connected uh, uh, most connected nodes and combine them together. And a simple way is to just connect two nodes together. That would be another algorithm. Try to connect two nodes that maybe these two are isolate from each other, or maybe it there will be an algorithm to decide the connection between these two and these two to another. So
Okay.
it is these two nodes will build up a community, which means the internal relationship will be stronger than the outside. So that two
Right.
nodes will be connect together. So this is two nodes connect together, but there were many different kinds of community calculation algorithm. I can't remember, but it is some mechanism that relate to graph zero. For example, there will be more internal edges, that which means there will be strong connection between these nodes, and there will be only one edges to the outside, so we can isolate.
Okay. Right.
Yeah.
Right.
It's
Okay, yeah. I was watching, I was trying to learn a little bit about graph neural networks, and I remember running into that. I need to go back and revisit it.
Yeah, and actually there are many different ways to do that. For example, we can decide according to some attributes of the nodes. For example, they are all belongs to a land cover. For example, the water or forest, we can regard them as one node with a coordinate. And maybe they have a similar hydrological structure. We can regard them as a one node. And
Right.
yeah. And actually, I'm writing a paper about the coordinate as coordinate, and maybe
Okay.
maybe at the end of mid of next month, I will ask some suggestion from you guys,
Sure.
and maybe it's about scale robust simulation of large scale ecological modeling. Many about
No, this is a very cool, it's a
many
very
about
cool topic because it's a fundamental problem, which is how much connectivity and, should you simplify? Do you need to add more?
yeah.
It
But
has a lot to do with model complexity and so on. Yeah.
yeah, that paper will focus on the grades, but not graph, but it's very
Sure.
similar. I can take a look later.
Sure.
Finish it. Thanks.
So my apologies, guys, but I'm gonna have to go because it's very late for me.
That's all from my side.
Yeah.
It's okay.